Now, let me move on and talk a little bit about what matters when we physically make an inductor. What are the areas we pay attention to and how does it work? And I think for today I will only have the chance to talk about metallization, and then we'll have different sections talking about other things. So in the metallization, the first thing that we need to remember is that you're always limited by some type of T, the thickness in the metal that you can use, but you're also limited to the width of the inductor. Of course, it's always a good idea to make a very wide turn, but then the inductance gets huge. The inductor gets huge, and again, that consumes too much area. Now, what is important, though, to remember is that at RF frequencies, there is the skin depth that will essentially dominate the inductance loss. And the skin depth is given by this equation right here, is this delta. Now, it turns out that if you actually run very accurate electromagnetic simulations where they literally mesh the metal itself and they actually calculate the current density in the metal, you will find out that this RS, the resistance per unit length given by this equation, is actually the best you can ever hope to get. So this is the minimum, in other words, resistance per unit length that you can hope to get from a design, and to get this, you actually need to make your inductance at least 2 skin depths. So to say it differently, if you can't even make the thickness of the inductor 2 skin depths, forget about the resistance in this green box. But if you can dedicate 2 skin depths for the inductance, then that's the minimum series resistance per unit length that you can basically get. And if you look at this equation, of course, it depends on W. So obviously, wide inductances are lower resistances, as we expect. It depends on the skin depth, which is a function of frequency. And of course, it depends on the conductivity of the metal. So what I show you in this graph is the calculated skin depth as a function of frequency, and the horizontal scale is logarithmic for 3 very common metals: aluminum and copper, that are used in many RFIC designs, and gold, which is used in many MEMS designs. So what is interesting to look at this from this graph is that if, let's say, I'm designing an inductor at 1 gigahertz, very, very common frequency for the inductor design, then I need something in the order of 5 to 7 micrometers, depending on what metal I have chosen, to basically get close to this value here. And that's hard to do. And so the way we basically do that is by typically electroplating our metal to the thickness that you see here. But it also teaches you that once you reach 5 to 7 micrometers, any additional thickness you electroplate is actually useless. So that basically works from both sides. So if somebody tells you how thick something should be, this is a good way to explain that. On top of that, there are 2 other non-ideal effects I want to very briefly mention. One is you should not forget about eddy currents. There are actually eddy currents in the metal itself that get excited, which basically means that the resistance you see here is actually relatively ideal. The real resistance would be lower than that because of the eddy currents in the metal itself. And secondly, you have also other issues such as non-ideal sigma and roughness. So what I mean by non-ideal sigma is the conductivity of the metal, and most of us will just open a manual and will say, what's the conductivity of copper or aluminum, and we'll write it down and plug it into that equation. The reality is that thin film metals have non-ideal sigma. Typically, they have conductivities up to 50% lower than the bulk one. So thin metals are not bulk metals. They have lower conductivity. And roughness is also a result of electroplating or any other process you use to build up the metal. And roughness can actually kill you if it's too bad. So the roughness, these equations assume perfectly smooth metal, but rough metals actually increase loss quite a bit. So usually what you will find out is that in real life, you're actually not even getting what I'm showing you here. But these are the 2 main reasons you're not getting it. And, but you can use this equation here as an upper limit to give you the best estimate based on just a simple algebraic equation that you can get.